In the next subsection of the sorting chapter, I want to talk about a lower bound. So I teasered this earlier and said computer science is fairly unique as an engineering discipline that we can prove lower bound statements that we can also attain. So we have matching impossibility results, and just in the realm of possible we can actually get. And so I want to show you this. This is the simplest example of such a bound. It's not so much that this bound in itself is the most exciting in the world, but it shows you the flavor of lower bounds. And there's many more of such algorithmic lower bounds. And I just think it's useful to have the flavor of how these work and their limitations. So what is a lower bound? It's a mathematical proof that no algorithm can possibly do better than some certain performance guarantee. So it's an impossibility result. It says nothing's better than X. I can always compare this to some elementary principles in physics, but I pointed out that we have much stronger lower bound than this in computer science. So often we can speak of optimal algorithms, even though that term is a little simplifying in that you have to be quite precise about what this optimal really means. But you can have an upper and a lower bound that match. So we'll come to that when we talk about this specific case here. Now, this is all great. So we like lower bounds because there are these definitive statements about how good algorithms can be. How can we get a lower bound? To prove a statement, remember Unit 1, like all this basic stuff, it's a for all statement, right? For all algorithms, the cost is at least this and that. So we need a way to formalize what this means, all algorithms. Now, we have a way to do that. Those are our language models. They are exactly doing that. So we could take our word RAM model and say every possible word RAM algorithm has such and such of a performance. This is the gold standard that we would like to have. It turns out this is quite more complicated or more demanding on the techniques. So instead we use a more restrictive model, which is also typical. If you can't seem to find a meaningful lower bound in some more general model, you look at some restricted one first. Not because that's the most relevant for practical purposes, but it guides you towards where exactly the hardness of a problem lies. In our case, this simple model will be the comparison model. And this is not too far away from how we define sorting in this unit. But we're a bit more specific about saying the only way how you can learn about the order of elements is by pairwise comparisons. So you can take two elements and ask which one is smaller, or strictly speaking, is A less or equal than B? That's the only query we are allowed. And the other part is not as essential, but we assume that we have one array of elements and we can swap them. That's the way of moving them. It's not as much of a restriction. But OK, I'll comment on what this does not allow. The cost in this model is the number of these operations, and we count them separately, and we will focus on comparisons. That's for this section at least. So the number of such comparisons, two elements, is A less or equal than B, yes or no? That's our main metric for success. In a way, that's a great model because it's very generic. Almost all algorithms we are seeing are of this kind. They can be formulated like this. So we like that. We have seen two examples. The model also makes some restrictions. So it for example, says we cannot take two elements and add them up, or take the average over all the elements in the array. That's not something that the comparison model allows. It only gives us this comparison operation. So we will see that this can be a restriction. But for now, that's the model. Merge sort and quicksort follow this. So we're not talking about the empty set of interesting algorithms, at least. Now, what's useful about this model is that it allows a apart from describing an algorithm as a program on a word RAM or similar models, it allows a different way to view a program if you just count the number of comparisons. So I'll say let's replace this with comparisons. In this subsection, I want to focus exclusively on those. If you do that, every comparison-based sorting algorithm can be seen as a decision tree, where we only keep track of what have we learned about the relative order of the elements. I'll show an example in the next slide. But a few comments. So this is completely ignoring the effort we have to move data around. But if we only count comparisons and everything else is for free, that's all right. And for the rest, let's see the example first. So here's one concrete comparison tree. It is a comparison tree for sorting 3 elements, and it's one specific algorithm. So just to see how this works, the algorithm first asks the first 2 elements in the array. Is A0 less than A1, less or equal? And there's 2 outcomes, yes or no. And then depending on the outcome, that's presumably in an if statement, the algorithm can do 2 different things, right? It can continue in different ways because it has to react to whether the element in position 0 is smaller. In this case, it actually does the same next question. The second step, the next comparison asked, is the same in either outcome. And it compares the positions 1 and 2. But this could have been different. In general, you're free to do different things in the different branches. And now let's just trace one of those branches down to a leaf. If 0 was less than 1 and 1 was less than 2, then the list is already in sorted order. And so we'll write this here in terms of this permutation of 1, 2, 3. That shows you the relative size of the original input. So it was already sorted. If you have it the other way around, 0 is bigger than 1 and 1 is bigger than 2, then it's inversely sorted. And the other 2 cases are somewhere in between and do require a third comparison in this algorithm. Okay? So that's one such example of a comparison tree. And now just a few remarks that we'll use straight after. Every of these internal nodes is one comparison that the algorithm does. And there's the 2 outcomes. So we have 2 different parallel universes depending on what the input is. In a way, every such comparison tree represents one algorithm on one input size, but all possible outcomes for all possible inputs. Okay? One algorithm, one size, all inputs of that size. What else? The next comparison can depend on the subtree. I mentioned that, even though our algorithm here doesn't make use of that much. It stops early in one branch. The outcomes are on the edges. And then the final point is the leaves at the bottom of the tree, they represent one potential ordering of the input. So we have a permutation in all the leaves. Okay, that's cute, right? That's a cute alternative way to represent a sorting algorithm. Why would we care? We can use this to simplify our thinking about this specific algorithm, but also about any algorithm. Because the powerful statement is any sorting algorithm that's comparison-based must correspond to such a tree. We may not know how it looks like in detail, but there is one. Every execution of the sorting algorithm on one specific input is following one path from the root down to some leaf. So the height of the tree is the worst case number of comparisons. Remember, height is number of edges, which is the same as number of these dark red nodes, and that's the number of comparisons. And height was the maximum number of such steps, so that's the worst case input. Now, how tall must this tree necessarily be? We remember from last unit we talked about binary trees at length, and we found that if we have L leaves, then, well, we talked about having a certain number of internal nodes, but you can translate that to the leaves as well. Every internal node must have 2 edges, and so the leaves must be attached to somewhere. A binary tree is always exactly one more leaf than internal nodes. So the two things are very similar in this sense. So if we have L leaves, we necessarily have a height that's at least log of the number of leaves. That's virtually the same argument as in the last unit. And now we can put these two things together. The assumption is we're making a statement about all correct sorting algorithms. We're not interested in bounding the cost of an algorithm that doesn't actually sort. But if it has to properly sort every possible input, it needs to have a branch leading to any of the possible input permutations. In other words, we need one leaf for all possible orderings, and the number of orderings is called n factorial. It's just you have n choices for where the smallest element goes, then you take that out, so there's n minus 1 choices for the second smallest, and you keep going. So n factorial is n times n minus 1 times n minus 2, blah, 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 all the way down to 1. I guess you have seen that before. So we need so many leaves. That means the height has to be at least log of that beast. And that's, again, log of n factorial is a fairly inconvenient function. But asymptotics to the rescue, we can express that in a much simpler way. For example, as a theta notation, it's the same as n log base 2 of n. Asymptotically, so in this sense, if you divide it, the ratio goes to 1. You can even be more precise if you want. So you can say it's this plus a discrepancy that is bounded in terms of order log n. We haven't talked about such more precise approximations, and I won't really use them, but some of you will have seen more stuff on asymptotics. So like, is this essentially just showing this? There's more behind this. You can get more precise asymptotic approximations if you want, or where it's useful. And so you may have been like, I may have dived deep in the details now, but this is it, right? This is our lower bound, because it means every correct sorting algorithm, at least in the worst case, must use asymptotically n times log n comparisons. So that's pretty cool, because that's a statement about all possible sorting algorithms if they're comparison based, and we can show something about their worst case, right? Now we can compare this with algorithms that we've seen, and for example, merge sort achieves exactly this up to the first order approximation, exactly the optimal best possible number of comparisons. We haven't actually analyzed it that way. If you remember, the result for merge sort I did have on the slide was 2 times n log n, but that was element visits. So if we visit an element for reading it in the merge and then for writing it, that counted as 2 visits because it's 2 different positions. But there's really just one comparison happening. You can always charge the comparison to the element that's written to the output. And so every element is written to the output in each merge just once. So it accounts for one comparison. That's the worst case, at least. OK? Now it turns out this is one of the things where we don't know much more. There's some recent paper trying this that's so complicated. I'm not sure if someone has understood it yet and checked if it's correct. Prior to that paper, at least, no one even had an idea whether this is easily doable. So if you want to be more precise and also get this next term of the approximation matching the lower bound, that's still a bit unknown. I don't know how excited you are about this bit, but I thought it's worth pointing out that even these very fundamental problems are not completely solved and can get quite tricky. Okay, a little innocent question, just to see if you're awake. So the question is, does the tree, I'll show you in a second again, correspond to an optimal, worst case optimal sorting algorithm for that input size? right? Remember, it's always for a specific input size. Okay, I have 57 or so people voting for the attendance code. So we should get at least 50. We're at 33. $44, $46. $49. Okay, 51. So it's quite interesting. Some a fairly even split. So let's see what's happening here. What does it mean to be the comparison tree for a worst case optimal algorithm in this case? So let's unpack that. First of all, we're only talking about size 3 because, as I said 500 times now, a comparison tree is only for a fixed size. So any proper algorithm, merge sort works for any input size. So for any input size, it would generate one such tree. They get fairly huge to draw because they're exponential in size. So I didn't put one on the slide for much larger. But they exist. Now for this specific one, we have 3 elements to sort. That's 6 permutations, as you can just count on the slide. Here they are. So we need to put those in the leaves. Now, if you just do the math, 6 is between 4 and 8. So log base 2 of that will be 2 point something. Rounded up is 3, right? So there's no chance with 3 elements to sort all permutations with 2 comparisons. It's not possible. The simple argument, if you have just 2 comparisons, you can only distinguish 4 different things. Simple coding argument, right? 0, 0, 0, 1, 1, 0, 1, 1, that's all. I don't get to 6, so I need to spend 3 comparisons sometimes. And so that's what the question was really asking. Does this tree have height 3? Which I guess you all know how to check. So the answer is yes. Which also shows you, like, for a very small number of elements, it's not so hard to find a worst case optimal algorithm. The challenge is to do this in the general case.